Hi, welcome back to physics. Today we're going to talk about the Newton's first law. So at this point, you're expected to have already completed a video tutorial from Khan Academy, as well as a reading an article from Khan Academy. So you have a basic idea of what Newton's first law is talking about. So quiz for you right now. If I were to ask you to pick out what is the keyword, the one keyword that you would use when we're describing the Newton's first law, what would it be? That's right, it's the inertia. And the next question for you is, what is directly related to inertia? Or another way to phrase the question, what is the physical quantities that can determine if something have a high inertia versus a low inertia? Yes, it's the mass of the object. Okay, so Newton's first law states an object stay in motion when it's in motion, and an object stay at rest when it is at rest. What does that mean? When something that is either at rest or something that is staying in motion remains in motion, meaning in another word, it's saying that it's traveling at a constant velocity. The implication is that when anything that is experiencing the Newton's first law, the acceleration is zero, right? Can you think about it, right? Something that's at rest or something that is constant velocity, not speeding up, not slowing down. It has an implication that the acceleration is zero. And the other thing that the first law is also saying is that, well, if something that is not accelerating, there is a given parameter that it has to fit. And that one is the F net, the net force. The overall net force acting on the object must also be a zero. So what does that translate to you when you're doing physics problem? In order for you to recognize that, oh, this word problem, it means that it is a first law question, there are two ways that you can be indicated. Say, for examples, the first type could be if they're telling you, they give you a bunch of forces, but they're saying, for example, they're like, oh, a force that is going upwards at 2 newtons and then another force that is going downwards at 2 newtons. You work out the net force, and if it worked out to be zero, the implication or the hint that they're giving to you is that, hey, if the net force is zero, I know the acceleration also has to be zero. And vice versa to that opposite is if the question give it to you that they tell you that, oh, you have an object that is at rest, is sitting on a table, or if you're of a car that is traveling at a constant velocity, it also tells you that means it's implying acceleration is zero. Then you also know that the net forces, the overall net forces acting on the object also has to be zero. All right, so let's do some examples together. So you can find this in a Google Classroom post, which is also the same as the package that we have been given you. This is lesson 3. We're just going through the examples together. And the question asked you, use the Newton's first law to explain each of the situation. So why does a computer sitting on a desk remain at rest? You can actually just say if it's remaining at rest, so implicating that because the acceleration is zero in this case, then you can say that it's because the acceleration is zero, therefore the net force acting on it must also be zero. And the requirement for any of these dynamic questions or the forces type of question is that you can always use a free body diagram to help you. And so to draw a free body diagram for a computer sitting on a desk, we would draw a box. We would draw all the forces that are acting on it. So the forces acting on the computer is going to be your force of gravity that's going downwards. But then at the same time, because it's sitting on a desk, it has the force of normal that is going up. And if it's at rest, then it's telling you that, you know what, the up force and the force down force always has to be the same. Next question. Why does a hockey puck moving across the smooth ice move at a constant velocity? Very brilliant and creative. The answer is also because the net force also has to be zero. Draw your pictures. A hockey puck. Hockey puck has force of gravity acting on it. Hockey puck is sitting on the ice. It has a force of normal. It is moving across the ice, moving at a constant velocity. What other forces must your puck be experiencing? It's moving. It has to have a force of friction that's acting on it. But if this is the only forces, it can't have a net force of equals to 0. So meaning this hockey puck probably have a hockey stick or a kid pushing it. It has to have an FA, and this force of applied force have to balance out the force of friction in order for it to be moving at a constant velocity. Next question. Why does a wagon pull across a rough surface by a child move at a constant velocity? Surprising answer. You're going to say that net force is equals 0 again, and to justify it, you draw pictures again. A wagon, force of gravity, force of normal. A child is pulling it, and it's going across a rough surface. The only thing that I'm asking you to check, if anything, do you have arrows on your picture? Are all your forces coming from the middle of the box? Do you have arrows above your forces? Question number 2. How do headrests prevent injury during a rear end collision? So, every time when you're dealing with questions that involve explaining, first thing I would suggest you to do is quote the law. Okay, this is, it didn't really say if the car is moving or not. So at this point, I'm just going to assume that the car was not moving. So the first thing I would say is state the first law. So according to the Newton's first law, object at rest stays at rest. Okay, and where does that lead us? I'm just going to write this out. Okay, so you got a person. The person is sitting, driving. Oh, let's change the color of the car. Okay, so let's say this car. It's the steering wheel, and there's your dashboard. There's this chair that he's sitting on, and then it's hooked up to, connected to, I don't know how to draw a car. So a car that's going like that. Okay, and the object was not moving. You're not moving at first. Okay, and when the car got hit from the back, the car is going to all of a sudden experience a really big acceleration going forward. So the whole car is going to experience a big acceleration going forward. So meanwhile, your poor head, was not moving. So the acceleration originally was 0. It was not moving at first. Sorry, I should have said the velocity of the head was 0 before. So what happened is the object at rest stays at rest. Your head wants to stay at rest, while the rest of the car, including the chair, want to move forward, causing your head to, looks like it almost moved backwards. Your head didn't move backwards, but the rest of your body is moving forward because your chair is causing you to do that. And so therefore, your headrest is actually allowing your head to move with your body. And that's why it actually stopped you from a very bad neck injury. Does that make sense? So your head wants to remain at rest while the rest of your body will accelerate very quickly with the car. The headrests will protect your head slash neck from pulling backwards. Question number 3 now, they're asking you to determine the missing forces from each of the free body diagram. So let's take a look at them. Question A says, they tell you that the object is at rest. So at the beginning of the video, we already mentioned, if they mention anything that is at rest, it's telling you that the acceleration is 0. And it's also telling you that that means the F net also have to equal to 0. Okay, go back to lesson 2 to follow the proper format of how to analyze a forces types of questions. So we would analyze it according to along x and along y. And because for this question, all of the forces are acting along y. So I'm only going to study this. I started the question always with F net. And then I have to summarize the net forces. Okay. And because it is at rest, there is no direction of which side is going bigger or smaller. So I know I talked to you about that. Do I go up minus down or down minus up? I don't know if you remember me talking about this yesterday, but if you don't, you need to just kind of go back. Because if the net force is 0, meaning the forces are balanced. So it doesn't matter if you go up minus down or down minus up. Okay, so that means in this case, I'm actually just going to go up minus down. I'm just going to move this here so I have a bit more room. Okay, so F net is equals to up minus down. Okay, and then the other part now is, what else do I know from the question? I know that F net is equals to 0. So that means this is equals to 0. So finishing solving the problem. So I now know 0 is 12 plus A minus FG. Rearrange the equation for FG. You don't have to write this next step out, okay? But I'm just going to show you just to make sure we're good. Does it make sense that I would have to move this over to the other side? It used to be minus, so I'm now moving it to the other side by adding. So FG is equals to 12 plus 8, which is 20 newtons. And don't forget the direction. Don't forget your vector sign, right? So the direction is pointing downwards right here. So we write the direction down. Part B, object moving at a constant velocity. Implications again. When it's a constant velocity, it means that it tells me that it's not accelerating. And therefore, according to the first law, if object is not accelerating, I know the overall net force have also to be 0. Analyze the force along x and along y. Studying the x force, F net equals to, all right, because then there's no acceleration right or left. Doesn't matter if you go right minus left or left minus right. So I'm just going to go right minus left. There's 2 forces along the left-hand side, so I'm going to subtract them. And since I know that the net force is 0, so this is 0. So 0 equals 28 minus 15 minus F1. Rearrange the equation. F1, bring it to the left-hand side, is 28 minus 15. So it equals to 13 newtons. And then look at the direction. F1 is going to the left. So I'm just going to put the left. I'm going to try to squeeze the y direction going up this way. Okay, y direction, there are 2 forces that are going along y. F net y is equals to up minus down. Since I know F net is 0, 0 is F2 minus 22. So I know that F2 have to equals to 22 newtons going upward.